So hello everyone, I'm Clayton. I'm coming all the way from Finland here. So I'm going to be talking about deep learning applied to human activity recognition and how we do things more efficiently in this area. So I will talk briefly about the introduction, motivation, then the methods, evaluation, and discussion, and conclusions. So human activity recognition consists in inferring what kind of activity, what kind of actions a person is performing from sensor data. And nowadays, shallow machine learning are being overshadowed by deep learning. First, there is significant leaps in performance when we use deep learning for that. And second, deep learning drops the requirement for hand-engineered features. For example, here's a picture of some data collection for the opportunity data set. We have about 113 sensors in the human, and doing shallow machine learning with extracting hand-engineered feature for all the sensors, all different types of sensors placed in different parts of the body for detecting some activities, it can be a long job. So that's the good point of deep learning, but also there is a bad side. First, it consumes a lot of energy. For example, nowadays we have batteries that are not lasting long, at least in my opinion. Also, there is high memory footprint and computational expense. But there is many research on how to port these deep learning algorithms into resource-constrained devices. And basically, this research is about reducing some redundancies. For example, by pruning some weights in the neural networks, by factorizing layers, quantizations, or even binarizing weights. So there are this kind of methods, I call them generic compression methods, and they have been used with human activity recognition with deep learning. So people have created some deep learning models for human activity recognition, and since they want to reduce the resource consumption, they use some generic compression methods. But here in this paper, we are looking into something different. We don't want to just take these compression methods and apply. We are looking into how deep learning is being applied for human activity recognition, and we want to see how we can improve that without using these compression methods. So here, I first talk about one thing in human recognition, human activity recognition with deep learning. First, for example, let's suppose we have data there, a data stream. But to be simple, let's say it's only one sensor. And what we do here is that we take a window, for example, xk minus 1, xk, at every instant we have a window. This window, for example, can have 5 seconds. And what we do, we feed this window to a neural network and it gets a prediction. So having a long sliding window there will give you a wider temporal context to better infer about the activity. But there is also downside because it increases the number of parameters in certain layers. For example, recurrent layers are very used in human activity recognition, and fully connected layers. So this is the bad side about using long sliding windows. Another thing, overlapping sliding windows. Well, here, for example, if our windows are 5 seconds long, if we don't use overlapping, it means that we have a prediction at every 5 seconds. So things might be slow in this sense. But if we use overlapping of 4 seconds, for example, we can have predictions at every second. So there is this point that overlapping helps to get more often predictions. Also, it helps when we have the training data. You segment using overlapping sliding windows. It serves as a data augmentation. But there is computational redundancy because every time you are feeding the same information, same data to the network, and you're performing the same things for this data. So this is a redundancy. Another thing here is that in some activities, for example, walking or running, you perform for 10 minutes or even more. Use deep learning to predict them. We are actually extracting the same features redundantly over and over for the whole duration of the activity. So that we are looking at. So we want to see how we can do pressure methods. So first of all, let's do, sorry. That's what we propose. The core idea of this, how we use short overlapping windows, sliding windows. So as we mentioned before, long sliding windows context. But here, we propose short. The whole purpose here is that, for example, we have a couple of an LSTM layer. This convolutional layer usually done in the literature. We train them and spatial context. Spatial context is the dependencies between the sensors. And the LSM layer here, we do something different. It is to learn inter-window temporal context. So we train this LSM layer with a sequence of feature maps output by the CNN. So this is the core idea of how to utilize short non-overlapping windows. And here in, overlapping, we still use overlapping as a data augmentation in the training, but during testing, since we have shorter sliding windows, we can actually have predictions more often, so we don't need overlapping here. And so this is on the left side, the literature's approach. We have long sliding windows with overlap. The network doesn't recall information from previous windows, so overlapping is needed when we want to have predictions more often. And now here we are using shorter sliding windows, and our network can actually remember previous information from different windows. So the third thing about the third redundancy we talked about, for example, in the activity walking, as I said, you can perform it for 20 minutes, for example. So maybe instead of through the whole duration of the activity, maybe when we start walking, when you detect the person is walking, maybe we can ask, is the person still walking, instead of asking what kind of activity is the person performing. So the first question, asking, is the person still walking, is simpler to respond than the second question, what activity. So what we do here is that we utilize less information to predict whether or not the person is still performing the same activity. If that's the case, then we save some computation cost, some computation here. If that's not the case, then we infer what activity is the person performing. So by having an activity that takes about 30 minutes, we can actually save a lot of resources in this way. So we are skipping fine-grained features here. We're using raw features to predict whether or not the person is still performing the same activity. So these are the ways we approach the problem here. And okay, so we're going to discuss about evaluation, the evaluation part. So we took some public data sets, PAMAP2 and Opportunity, and we take a baseline network, CNN LSTM, that uses long sliding windows and overlapping. And also, we take one of the state-of-the-art networks using inception networks in OHR to compare with them. So we have a couple of metrics. F1 score, we don't use accuracy. F1 score is more used in human activity recognition because we have more imbalanced data sets. We also want to know what are the number of parameters in the neural networks, the total computational expense in predicting the activities in the test set, the number of activities, the number of predictions over the entire test set, and also this new metric. This new metric has not been studied before, I think, to the best of my knowledge. It's about how much data do you need before predicting an activity with before correctly predicting activity. So let's go to some results here. We have first the baseline CNN LSTM that uses long sliding windows with overlapping. Then we have CNN LSTM with short non-overlapping sliding windows, second one. The third one, CNN LSTM with short non-overlapping sliding windows with utilizing raw features for detecting long-lasting activities. And we have InnoHAR there. So we have two data sets, PEMAP2 on the top and opportunity on the bottom. So what we actually notice is that our performance improves over the baseline, and it actually gets pretty close to the InnoHAR, and in the opportunity data set, we got even a better score for that. So, and we get this, compared to InnoHAR, we have like 2 to 3 orders of magnitude less, fewer parameters and less computational expense. Oh, sorry, I think I didn't mention, but F1 score on the left, number of parameters, the number of predictions, the total computational cost in gigaflops, and how many seconds of data you need before correctly predicting activity. So we actually, as I said, have 2 to 3 orders of magnitude less, fewer parameters and less computation expense. And also, there is a significant reduction compared to the baseline when using long sliding windows with overlapping. Also, this metric that we introduce here, the last one on the right, it means that we need less data. With our method, we need less data to correctly predict an activity. So in some cases when, for example, you use human activity recognition to detect if a person is doing the right thing, the sooner you detect what the person is doing, the better it can be. If the person is doing something wrong that you don't wish they would do, this can actually save. So as I said, there are faster predictions of new incoming activities. And, well, we have done all of this without relying on compression methods. So, but we would like to see how our work can be merged with compression methods in the future to get even better results, probably in terms of research efficiency. Okay, so some conclusions. The most common approach in human activity recognition is to use long overlapping sliding windows, and this affects negatively research efficiency. So we propose to use short non-overlapping sliding windows and to skip fine-grained features during long-lasting activities. So our proposal delivered comparable performance with the state of the art while being improved in terms of research efficiency. So that's about it, if you have any questions.